Is my screen visible to you?
Yeah.
Okay, so we will start now. So good evening, everyone. Today it is the eighth live session for basic environmental engineering pollution and abatement course. And so far we had discussed few um, design aspects and treatment procedures for air pollution, and also in the last 1 or 2 weeks the treatment strategies which are used for wastewater treatment. Can you please mute yourself? Yeah, so
Ah,
please
correct.
mute yourself. Yeah, so in this class we will be discussing few tertiary treatment technologies, and so far we had discussed excuse me. Yeah, so this is a technology where which is used kind of biological treatment where we use some sort of microbes, and also we try to generate electricity through it, and which is nothing but microbial electrochemical cell where biodegradable organic matter is not only degraded but also some sort of electrical energy or some hydrogen is formed which can be later used to produce, which can be later used as fuel. Okay, so here first is microbial fuel cell, and here the electron transfer mechanism is, it can be indirect or it can be direct. So what happens is here, this is the inlet of water, and there will be two chambers. One is anodic chamber and another is cathodic chamber. So now this is the electrode, anode and cathode. Now the reaction takes place here where organic contaminant is degraded. So the end product will be CO2, and CO2, since it is gas, it can be liberated out. Now, due to the reaction occurring here, there will be some amount of release of oxygen. Okay, so that released, sorry, not release of oxygen, but some amount of electrons which are generated here at NO, right? Which is due to the degradation of organic contaminant here. So uh, here what happens is these electrons are responsible for, like if we connect this to an external circuit, these electrons will be responsible for electricity generation, and some sort of or some amount of voltage or current will be obtained. Now that can be used outside. Now H plus will also be generated, and this is a permeable membrane which allows only H plus to pass through. Now this H plus, when it goes to the cathodic chamber, so here the reaction occurs to form this H2O, and oxygen is supplied here. So this is the overall mechanism. Now the electrons which are produced here, it can be due to indirect method or it can be due to direct method. And in indirect method, there is some uh, external agent required which will be able to pass or able to convey the electrons, while in direct transfer, it the microbes or so they are able to directly uh, transfer the electron to the like from the solution. You need some way so that it is passed to the anode and later it will be forming a circuit. So now hydrogen, as I said, hydrogen transfers through this um, permeable membrane where hydrogen ion it will be uh, conjug- uh, side by side reacting with few molecules and to form H3O plus, and it will move to the other side. Now here the parameters like electrode material, mainly the material used here for anode and cathode, it can be some carbon or graphite form or some other materials. Mainly carbon or graphite material can be used. So uh, electrode material, what electrode you are using, the pH at which the operation is occurring, the electrolyte along with what wastewater you are adding, the proton exchange system, which is this membrane, then the operating conditions, substrate is nothing but the microbes that you provide here for the degradation, as well as the catalyst, which is because catalyst can speed up the reaction. So all these parameters affect the efficiency and um, affect the efficiency and what type of degradation you can achieve, and also what amount of voltage you can get. So based on that, what amount of current or what amount of voltage that can be obtained has been calculated during the class. Also, the types of this cells can be single chamber, it can be double chamber. Double chamber will have two chambers which are separated by one unit, and here there will be a membrane, and again here there will be another chamber. So this is anode, this is cathode. So there will be two chambers and there will be some bridge which is allowed to connect two chambers, and a membrane will be there. So this is very common. Then there can be flat plate, there can be membraneless or upflow. Now another is MEC, electrolysis cell, where what you do is you try to generate hydrogen in the process, and when you recover that hydrogen, that can be further used for fuel or generating electricity or so. So now moving forward, next processes that are um, involved in wastewater treatment are tertiary treatment. So far all these methods were secondary treatment. Okay, so briefly, primary treatment is majorly considering uh, suspended solids, porous solids, right? There can be some amount of organics that can be removed. There, now during secondary, majorly we take into account organics and these are removed. Now during the tertiary treatment, so this is generalized, okay? Both these are generalized. Obviously, from industry to industry, this can vary, but what happens is there will be certain particular type of pollutants also present in wastewater, and to remove those, even if they are in traces, they can cause hazardous effect. So remove those. So to remove those traces, depending on what type of pollutant they are present, we have final stage to remove specific pollutants, which is tertiary treatment. And depending on the type of pollutant, we select the type of tertiary treatment. So some of the few examples of tertiary treatment which are discussed here are adsorption, then membrane separation, and advanced oxidation process, right? So let's start with the adsorption process. So can anyone give me brief what is adsorption? I guess I had given you some idea what is adsorption. Yes, anyone?
Absorption is a surface phenomenon where gas, fluid and solid phase.
Yeah, correct. So it is a kind of surface phenomena where if you have a solid, then any fluid, it can be liquid or it can be gas, then certain type of molecules will adhere to the surface of solid, and there will be some sort of force between these two which helps in uh, attraction of these particular molecules to the surface. Now, these forces can be physical forces or it can be chemical forces. Now, right here we are just concerned about liquid. Okay, so liquid is here. Say, for example, if you have wastewater, then it can have pollutants in the form of, let's say, some amount of organic is left. Then it can be heavy metal. Then there can be some pathogens, right? So for different types of pollutants, if they are present, then what adsorption will do? It will try to attract these pollutants and it will, and obviously not water. So it will try to attract these pollutants and they will adhere here on the surface. So some examples of physical forces are van der Waals force of attraction. Okay, there can be some hydrogen bond or there can be some chemical bond also, right? Chemical bond can be covalent bond. Covalent bond is very strong, but still some chance. Then there can be coordinate covalent bond. So these are few examples. Also, there can be some electrostatic force of attraction. So now let me take a new slide. So let's say this is the piece of solid. Okay, and these circles here are representing the pores of that solid. Now, this is the pollutant which is present in the bulk of wastewater, which is to be removed. So, firstly, the steps for adsorption, it involves first is the bulk motion. Okay, so from anywhere in the bulk, it has to travel to the surface or near to the surface of the solid. So, bulk transfer of pollutant to solid surface is the first step. Now, once it comes near to the solid surface, there can be pores and it has to reach to the or near to the active sites because through the pores also it can go deeper inside. Okay, so internal diffusion, and once it comes near to the contact of active sites, then the active sites are nothing but, can define here, active sites which um, sites on the adsorbent surface which binds with adsorbate, right? Adsorbate is the pollutant here. And third step is the adsorption on the surface, right? So these are the steps involved for adsorption. Now coming to the factors affecting the adsorption process, these include temperature, concentration of pollutant as well as what amount of adsorbent is there, then the contact time, pH of solution. So let's see here. So what is the role of temperature? So for example, temperature, it can favor adsorption can be endothermic. Mostly it is exothermic process, which endothermic or exothermic process, and mostly it can be told as exothermic process. So if we increase the temperature, then it will result into desorption at higher temperature or approximately at room temperature adsorption occurs. Okay, so this is the effect of temperature depending on the type of or nature of adsorption, may it be endothermic or exothermic. If it is exothermic, majorly which is the case, then room temperature will favor the adsorption because at higher temperature the molecules or the pollutants will have higher energy so that it can overcome the forces which are exerted by the adsorbent on the adsorbate so that it can escape from the surface. Another is the concentration of pollutant. Now, since you can say if there are four molecules here, then only four will interact with the active sites. Now, if I increase or decrease the number of these pollutants, then if on increase in the pollutant number, then the interaction will increase, and obviously the amount which is adsorbed on the surface will increase, and vice versa. So, hence we can say that concentration of pollutant also plays an important role. So, more the pollutant, more will be interaction between adsorbate and adsorbent, hence better adsorption. Similarly, concentration of adsorbent also plays an important role because more the amount of adsorbent you are taking, more will be the active sites will be present, and hence more adsorption can occur. Third is the contact time. So contact time initially, since more and more initial phase. So let's say this is the adsorbent surface and these are the active sites. Now these are the pollutants. So you can say initially during the initial phase, majorly vacant sites are there, right? So any like pollutant has chance to bind with any of these, right? So it binds here. Now when more pollutant comes here, so the amount of active sites gradually reduces. So here now the adsorption speed decreases. So initially it is fastest, gradually the speed reduces, and once majorly all the sites are filled up, equilibrium is achieved, right? So you can say as you increase the time, uh, initially The speed or initially the uptake or removal is high. Gradually it slows down and it attains equilibrium. And the last factor is pH of solution. So pH can affect the forces that can prevail between adsorbate and adsorbent. For example, if the pH is in acidic range, then it ensures that the surface is positive, and basic means surface will tend to be negative. So to have electrostatic force of attraction, then if surface is positive, then negatively charged pollutant can be absorbed, and if the surface is negatively charged, then you can absorb positively charged pollutant for electrostatic force. Now there are key terms which are there for adsorption. First is the specific uptake capacity and the adsorption capacity, which is calculated as the milligrams of adsorbate or pollutant here, which is adsorbed per gram of the adsorbent. And here you can, for specific uptake calculation, there are various isotherms which are discussed during the class. For example, Langmuir, Frundlich, and there are many more. For example, Temkin or in DR. But majorly, you can say Langmuir or Frundlich are the ones which are used. Now, this will tell you from this you can say whether the what is the kind of or what is the nature of absorption taking place based on what the assumptions are included during the model's formation. For example, Langmuir says that adsorption occurs due to chemical bond. Okay, so you find out what is the better fit and you can suggest what is the nature of adsorption taking place. And also you will be able to find out what amount of maximum you can adsorption can occur onto the surface of adsorbent. Now another is the kinetics because you need to know what time you should provide for between the adsorbent and adsorbate so that maximum adsorption can take place, and also further you need to have some continuous removal in industrial scale, so at that time you need to have some proper contact so that also obtained efficient removal at low cost. So this will help you optimize the industrial scale removal. And last but not the least, spent adsorbent regeneration, where you can say that once the adsorbent or the pollutant here comes on the surface of adsorbent, you can say that now the toxicity from water has transferred onto the surface of adsorbent. So here you need to either have recovery of pollutant so that you can elsewhere use both pollutant or it can be recovered into some useful form, and also the adsorbent will be recycled and it can be further used for again the next cycle of adsorption, recovery of pollutant and recycle of adsorbent. Now once you recycle the adsorbent, as the number of cycles you keep on using the adsorbent, the amount of adsorption or the efficiency of adsorption keeps on reducing. Okay, so there will be one stage where adsorbent has to be discarded. So at that time, last step is you dispose it in landfill site. Okay, so now moving forward to batch and continuous modes of absorption. So batch will obviously give you specific uptake and kinetics, right? Now, but in industry, you will not be able to use this batch process you because there will be lots and lots of wastewater to be handled. So here, what we do, we use continuous columns where adsorbent will be packed inside the column, right? This is the packing of adsorbent, and you can have the flow. Let's say if this is the inflow, this is the outflow, then the uh, pollutant will come in contact throughout the column with the adsorbent and it will be adsorbed onto the surface and purified water will be obtained at the outlet. So here there is one terminology which is known as mass transfer zone. So what happens is once the pollutant or wastewater comes into the inside the column, then depending on the concentration of and the length of obviously the length of column, there will be a certain region where, say for example, this is the maximum concentration of C by C naught. Like this is the outlet C and C naught is the initial concentration, then it will gradually decrease, right? And so for that particular inlet, if this is the inlet time, then it will absorb only up to this much. Now, after that, it is not being utilized. So you can say that the absorption into the column occurs in the form of a front, like it will occur in the mass transfer zone itself. And once this mass transfer zone is completely saturated, then again it will move forward. So this zone will be next, which will be taking care of for the removal and so on. So you can say uh, front or mass transfer zone is found to move in a downward direction, which has some speed. Okay, so the length of operation, this is nothing but empty z. Now what happens is it will go on reducing and there will be a certain point, right, after which there is no maximum uptake has been happened, and say for example after this point, till this point there is no pollutant coming out because here there is some enough space which is enough time which is available for contact and removal. So after certain point there is some sort of pollutant which is coming out in the influent. So now you do not want that, so it will start growing, and at the end, this will be C by C naught maximum. So the time at which this uh, C by C naught is greater than 0.05, then this you can say that it is the breakthrough, and you can say the bed has started saturating and more. Now further, you cannot have great removal efficiency, and also you do not want the pollutant to be in the outlet, so you this is the time till which it is advisable for you to operate, right? Uh, so I have mentioned you about this stoichiometric front, which is nothing but the mass transfer zone, or the front you can say it moves because there is only particular region where adsorption occurs. Now, as I mentioned, there will be after some point the pollutant will start appearing in the effluent, and there will be some zone where adsorption do not occur. So, as I mentioned, that adsorption occurs or the concentration reduces in this manner. Okay, this is the length of the bed. So, as you go on increasing length, the concentration reduces in this manner. So you can say this is the utilized bed and this is the unutilized bed. So in one mass transfer zone, you can say there will be some S-shaped curve form, and this lower portion will be used and upper portion will be unused. So if you consider ideal case, then this will be equal. Okay, right? So you can say that length of unutilized bed which will be remaining, it will be mass transfer zone, thickness of mass transfer zone by 2, right? Or length of unutilized bed is nothing but the length of bed minus the length of saturated bed which is consumed. Breakthrough time I have given you, like this is the time after which the pollutant starts appearing in the effluent and the concentration in the effluent per unit inlet concentration is 0.05. Okay, so these calculations are important for adsorption process and especially for fixed bed adsorption. Now coming to the ion exchange process, ion exchange is also taking place in the columns only. Now ion exchange is, I had mentioned earlier also, it is majorly for the removal of hardness. Hardness is for ion exchange is for hardness removal from water, which majorly includes calcium and magnesium. But apart from that, you can remove some other cations, including sodium or anions like chlorine, sulfate, right? So these type of pollutants can be removed. So I'm writing just the example of reaction which can happen. So for example, if you want to remove the hardness, then you can use such type of resin, ion exchange resin, which will be reacting with Ca2 plus or Mg2 plus to give you R2Ca or R2Mg, right? And to regenerate this, again, you need to use some sort of sodium salt, NaCl or NaOH to regenerate the bed. Now, for anions, you can use some sort of your R can be replaced. Okay, so that sort of pollutant resin can be used. Now, moving forward, another type of tertiary treatment which is discussed is nothing but membrane filtration. So, membrane, as I have mentioned or given you some brief, is nothing but a porous or thin sheet which has the tendency to allow only certain type of materials through it, and it retains some type of material. So depending on different characteristics of materials which are present in the wastewater stream, you can say here, so it will be able to pass some amount and it will be able to reject few types of material. So for example, it can work on different mechanisms, which is nothing but size based separation, which is the most common one. So where, say for example, you have different types of membrane which works on size based separation, which is microfiltration, ultrafiltration, nanofiltration, etc. So here, say for example, you have ultrafiltration membrane. So if these are the pores and you have bacteria to be removed. So now this bacteria is of 2 micron almost size, and the size of maximum size of these pores um, on the ultrafiltration membrane can be 1 micron. So you can say that since this is bigger in size as compared to the pore size here, then this bacteria will not be able to pass through the membrane. So this is the mechanism for size-based separation. So here what happens is bigger pollutant as compared to pores are rejected, right? So here you can say this by this manner pollutant can be removed. Now water has obviously smaller size, so water molecules can be passed from this pores and you can get here clean water, and there will be some reject, like water will pass through this side and permeate will pass through this. Now this clean water is known as permeate, and the one which is having a major, like it will pass through this. So here it will be concentrated wastewater, which will have higher, even higher concentration of that pollutant. So this is known as reject of that membrane. Now another is size based or diffusion based, which commonly works in RO membrane. Okay, so RO you can say there is a dilemma on it whether it can be classified into porous membrane or non-porous membrane because the size of pores are very small in that. So in that case, you can say that all the type of even very small pollutant or ions, you can say sodium ions are very small. Even those ions can be removed by RO. And RO is the most common. You would have heard that mostly all home filters nowadays, household filters, they have RO filters. Now RO, since you can say it removes even sodium, calcium. Now these are the nutrients which are present in water, and as they are required for our body, so household filters even they incorporate some nutrients addition after RO because it even removes minimum concentration of sodium, calcium in every such ions. Now another is ion charge or diffusion, which is nothing but electrodialysis. So electrodialysis, one of the most common example for electrodialysis is um, for your kidney, when your kidney malfunctions, then we the human is undergoing dialysis where this type of membrane is used where electrodialysis occurs. Now there can be temperature based gradient also can be occurring, for which membrane distillation is sort of the example, where you provide some sort of temperature gradient, and depending on the difference in the pressure or the water vapor, there will be some travel of water vapor through the membrane, right? So these are the types of membrane. Now coming to the classification based on the material of membrane, it can be organic or inorganic membrane. Now organic membranes are nothing but they are polymeric membranes, and inorganic are some sort of Al2O3 or ceramic membrane. Some metals will be used. So you can for polymeric membrane, now they have lower range of temperature operation, and also the operation in the pH range. For example, the pH of water should not be very acidic or very basic, otherwise it will degrade the polymer. And for inorganic, you can say the temperature, working temperature, and the working pH range are much more wider, but it is very difficult to prepare some ceramic membranes, and also they are costly. So in that case, polymeric membranes are much more used as compared to inorganic membranes. So here, the important terminologies corresponding to any membrane are nothing but retentate or nothing but reject, you can say. So this is so if this is the membrane, water passes. This is the feed water. So there will be some amount of water which will be passed through the membrane, which is permeate or clean water, and this is the reject or retentate, which is concentrated water. So this needs to be taken care of before you discard it. Now, even you sometimes need some carrier for passing passing the water or some sort of gas. The sweep is a type of carrier if you are using to allow certain molecules to pass through the membrane. So that is nothing but sweep. And barrier is nothing but the membrane which you provide the barrier for removal. Now, the types, the membrane can be fixed or the modules which can be used for membrane filtration. It majorly they are four. So first is the tubular membrane. So you tubular or the cylindrical membrane because they are not flat sheet, they are in cylindrical form. So there is one bigger tube and there is one, small tubes of membrane which are placed inside. Now the water passes inside and if it passes through the inside of the tube, then reject will come out from the inside of the tube and the permeate water will pass through the membrane and the outer or the annular region of this bigger and smaller tubes. This annular region will have permeate. Okay, so from the annular region you can have permeate or clean water. Now, next is the hollow fiber membrane. So this is the image of hollow fiber membrane, and hollow fiber is nothing but the this you can see the diameter of this cylindrical membrane. They are very thin, so they are similar packings only, but here the diameter is big. Here the diameter will be very small. So here you can have low flux of water. So similar you can observe if this is the arrangement of membrane. So if this is the inlet of feed and this is the annular section in which the membrane is arranged. So if this is the feed, then the permeate will from this annular space permeate will be obtained and from the inside of the hollow fiber membrane you can get the reject or some vice versa case can also be obtained where from the annular space you pass the feed and um, here from the inner space you can have the permeate. Another module which is very commonly used is the spiral wound module where membranes are rolled over in a spiral manner. Okay, so here there are spacers used so that membrane do not stick and you are able to separate each membrane. So, say for example, if this is the path of the membrane path in which the feed water is passing, then the feed water will pass through the membrane and you can have the permeate in the downward side and obviously you by this uh, carrier material you give the path in which permeate water will be allowed to flow. Okay, so it will go this side and it can be collected some outside. Now this is the reject and later you can collect the reject like this will be the direction where it passes. Now this is the most commonly used in household and even in industries like this is very common module. Another is the plate and frame module, which is not so common. And here, as you see, between the two plates, and there is a plate which is given as support between two membranes, and there will be some space through which feed water passes. And this water will be allowed to pass through the membrane. Like if you provide pressure in this direction, then permeate will be obtained from this direction and reject in this direction. Now there are some pros and cons of each of these modules. So, for example, uh, after a certain time, each of this membrane will be required to be replaced or cleaned. Okay, so cleaning in spiral wound and hollow fiber membrane, it is very difficult. Okay, and if you take into consideration the amount of flux or the clean water that you are getting from each of these modules, then flux obtained from the hollow fiber membrane, it is the lowest. However, the surface area for the removal or the efficiency of removal, which can be obtained from hollow fiber, it is the highest because more and more surface area is obtained due to the small diameters of the hollow fiber membrane, which is why better efficiency is obtained. So you need to depending on your application, you need to select wisely. And however, hollow fiber membranes are so far not commercially used in industries, but majorly spiral wound or tubular modules are used. So now coming to the next tertiary or the last tertiary treatment, which is discussed in the class, which is nothing but advanced oxidation process. So here, advanced oxidation process is mainly used because there will be some organic compounds in the water or wastewater which are not easily degraded by bacteria or which are not easily degradable. Say, for example, pharmaceutical, pesticides. Okay, so these type of hard to degrade organic compounds, they in the form of pharmaceuticals or some pesticides. So we need some extra strong oxidizing agent so that they will be easily get oxidized into final form, which is CO2 and H2, right? So here some of the strong oxidizing agents can be radicals and which is common as hydroxyl radical. Now radicals, as you say, since they have just one lone pair of electron, like one single electron, and which is the highly unstable state. So in that case, such hydroxyl radicals, they will be very much reactive in nature, which will tend to go onto the any organic uh, pollutant, and obviously some chain reaction will occur, and at the end you can have CO2 and hydrogen. Sorry, water. So there can be different methods where you can have. We can use UV to disintegrate H2O. Now UV adds on to the process. H2O you can H2O2, which is hydrogen peroxide, you can have two hydroxyl radicals. Okay, so depending on what type of oxidant you are using, you can have different chain reactions. So end product or the main motive here in this advanced oxidation process is to generate hydroxyl radical. So different types of methods are you can use H2O2 where two hydroxyl radicals are formed, and this hydroxyl radical formation can be enhanced by using UV because UV will provide some excess source of energy which will result into faster formation of hydroxyl radical. Now, next is HOCl. Also, this can form hydroxyl radical and chlorine radical. Okay, and even this can be further enhanced by UV. So, any of this membrane, advanced oxidation membrane, they can be used alone, or they can be added up by UV, which will further enhance its efficiency. Third option is the ozone-based oxidation process where ozone it can give you O2 and it will use up one molecule of water from it, and at the end, like this is I am saying not intermediate steps but end product, then you will have hydroxyl radical. Okay. So there are different reactions depending on what reagent you are using. Then coming to Fenton treatment, here you use Fe2 plus in H2O2. Okay, so here you will get Fe3 plus and OH radical. And again, there is a cyclic reaction where Fe3 plus will again get converted to Fe2 plus and one more hydroxyl radical can be obtained. Right? So depending on reagents you are using, there can be a different mm, reactions taking place. Now, one of the most common drawback of Fenton treatment is there can be generation of large quantity of toxic sludge. Now, this toxic sludge can be iron sludge or any of suspended solids which are formed during the process. So that toxic sludge needs to be taken care of. So this is the Fenton process, and even this can be further enhanced if you use UV here. Now, next is the photocatalytic oxidation process. Now, the photocatalytic oxidation process are nothing but you can say you must be knowing that any sort of semiconductor material they have two bends and which is nothing but any material has valence and conduction band. Now, the electron from this, if it is able to move to the conduction band, so for that you need some light, H nu. You can use some sort of a natural light source, solar light source, or you can have some artificial source of light. Say, for example, if you are using TiO2, it is a common example. So, electron will pass to the conduction band and here it will left hole. Okay, so now this electron in the conduction band it is not in the ground state and it can further be react and it can use up the water molecule and so on to form hydroxyl radical. Now again this hydroxyl radical will further um, uh, degrade the organics. And the light driven process are nothing but you add up UV or any sort of energetic light like UV has very high intensity of energy, so UV is the most common source of light. So and you combine it with any of the process for further degradation. Now how this OH radical reacts with any of the organic in the class, there is an example given of benzene, where OH radical it acts upon the benzene ring, and later it can be the ring opening first occurs, and later it can be degraded into CO2 and H2O. So this is all about advanced oxidation process. So if you have any doubt so far, you can let me know, or else we can proceed to the assignment. Okay, so if not, let's proceed with the assignment. So the cell voltage of microbial fuel cell could be written as dash.
A.
Yeah, so A is the correct answer here. And if you say what each of these terms are, so here I have given to you. ACT is nothing but the losses which incorporates the activation of any sort of gases because there will be gases CO2 and A2, O2. So activation of those gases in the interface between electrolyte and electrodes, there can be some utilization. So that is activation loss. There can be concentration loss, which can be there will be gradient in the electrolyte or there can be uneven depletion of the reagent. So there will be non-uniformity inside the chamber itself, which causes some sort of losses. And also similarly pH difference in the chamber because you can say that anodic chamber produces H plus while cathodic chamber it consumes H plus. So there will be a huge difference in the pH at which anodic and cathodic chamber they are operating. So in that case, there will be some loss due to that also. So the A is the correct answer here. Now identify the factors which affect the adsorption process.
D.
Yeah, all of the above is the correct answer, and I have given you each and like the detailed explanation how these affect the absorption process. So all of the above is the correct answer. Next is dash is used to remove phosphorus particles from water.
Alum.
Yeah, sorry, alum should be the answer. Let me correct. Yeah, alum is the correct answer for the removal of phosphorus from water. Now, pore size in microns of the membrane required for reverse osmosis is dash.
10 2.2.
No, it is this.
D.
Yeah. So here you can see this is the micron scale range. So microfiltration, this is microfiltration, MF, which is having the highest pore size in terms of membrane. Then there can be ultrafiltration, there can be nanofiltration and reverse osmosis, which has least pore size. And this is the, uh, you can say, what type of pollutant or material you can remove by any of the membrane. So, reverse osmosis, you can say all can be removed. Okay, so by using reverse osmosis, any such pollutant can be removed. Yeah, so D is the correct answer here. The formula can express the hydraulic diameter as dash. So here, total 4 into volume available for flow divided by total pore surface area is the correct answer. So can anyone tell me why do we need to calculate the hydraulic diameter? Okay, so pores inside a membrane, they are not exactly spherical or they are not exactly cylindrical. They are a kind of finger-like shaped, fingers-like shape they have. And to have that shape factor included for that calculation, we choose hydraulic diameter. Okay, so it will represent the path can be obtained through which it will be passing or the water or like it will show or denote the path through which water can be allowed or it can be passed. Next is the advanced oxidation process are the treatment procedures that generally uses dash for the remediation of organic and sometimes inorganic contaminants in wastewater.
Hydroxyl radicals.
Yeah, hydroxyl radicals is the correct answer, and this is the one reagent which is generated in every process, advanced oxidation process, which is responsible for degradation. Now, can you tell me why, like it is discussed in class, why only hydroxyl radical is suitable, or we have chosen hydroxyl radical over some other oxidizing agents? There can be some other radicals, or there can be some another oxidizing agents like ozone or so on. So, why have we chosen this? Okay, so let me tell you, any of the oxidizing agent, they have some oxidation potential. Now, this oxidation potential is the representation of the extent of oxidation that can occur, or how easily it can oxidize. Okay, so if you compare the oxidation potential of hydroxyl radical with any other oxidizing agent, then oxidation potential or the extent or of oxidation that hydroxyl radicals can provide, it is the highest as compared to others. So that is why we have chosen hydroxyl radical. Now, next question is identify the process given in the figure.
photocatalysis,
Yeah, so this is the photocatalysis process where this is the semiconductor, and when you incident some light, okay, so there will be excitation of the electrons. Now, these electrons are responsible for the conversion of O2 into O2 minus, and later here these holes are responsible for generation of this hydroxyl radical. Okay, so which will further degrade the organics. Next question is out of the following condition, the condition for size exclusion effect is dash. So here you can say dm as the molecule diameter. Okay, dp is pore dia. Okay, so if you want the size exclusion to occur, then dm should be greater than dp, right? So this should be the answer. And Kr is the constant which should be 0 in that case. So Dm should be greater than Dp and Kr should be 0. Right? Now next question is find water flow rate in meter cube per meter square day when it passes through a porous polyethylene membrane by a pressure differential at 70 degrees Celsius. Now the membrane has 25% porosity with zero point 0.6 micron diameter pores and tortuosity of 1.5. Now the pressures on either side of the membranes are 500 kilopascal and 125 kilopascal. Assume the membrane is 2 microns thick and flow is fully developed laminar flow. Find the flow rate. So let's start with this question. So here you had one formula for N, which was nothing but formula for finding out the flux. Now flux is always in kg per meter square, okay, per meter square second. So now if you want to have this in this flow rate, then you need to divide this flux by density, right? So to find out flow rate per unit area, you need to calculate this N by rho. Okay, and that formula will come out to be epsilon d square p naught minus pl 32 mu lm tau. Now, if you look into the values which are required and the question if you look into, so you have almost all the values. So here epsilon is what? It is porosity. Porosity is given to you as 25%, right? So which means it is 0.25. You do not need to use percentage. So porosity is 0.25. Then D is the diameter of pores, right? So D is given to you as zero point 0.6 microns. So which is zero point 0.6 into 10 to the power minus 6 meter. So you maintain a constant unit throughout so that it is easier for calculation because otherwise it will not be correct. So P naught is the, if this is the membrane, Then you are applying some pressure here so that there will be flow of water through the membrane. Okay, so that is the P naught is the initial pressure that you are applying. So P naught is kilo 500 kilopascal, which is 500 into 10 to the power 3 pascals. Now pascal is the SI unit, so you do not need to convert into any other. Then PL is the other side pressure on the other side of the membrane, which is 125 kilopascal, and it is nothing but 125 into 10 to the power 3 pascals. Others, what is required is mu. So mu is nothing but the viscosity. Now that is not given to you, I guess. So that you can take as 0.0042 Pascal into seconds. Now this will be the SI viscosity in the SI units. Then Lm is the thickness of membrane, which is given to you as 2 microns, which is 2 into 10 to the power minus 6 meters. And tau is the tortuosity, because there will not be any uniform path of force which will be followed by the water. So there will be some random motion of through random force, uh, which is accounted by tortuosity. So here that factor is 1.5. So if you put up everything, so epsilon is 0.25 into zero point 0.6 into 10 to the power minus 6 square into P naught is 500 minus 125. You take out 1000 common, 10 to the power 3. Now divide this entire term by 32 into mu is 0.00042 into Lm is 2 into 10 to the power minus 6 and 1.5. Now here everything is correct, everything is in meter, but the flow rate is asked to you in per day terms, and here the viscosity which represents time here, it has second term here. So if you want to convert that second into day, so 1 second is 1 by 24 into 3600 day, right? So if you do that conversion, so this will be multiplied by 20, numerator will be multiplied by 24 into 3600. Divide this by 32 into 0.00042 into 2 into 10 to the power minus 6 into 1.5. Calculate this. The answer should be B, 72321.43. Are you getting this?
Yeah, 72321.
Yeah, okay. So B is the correct answer. Next question is 100 ml of solution containing 20 milligram per liter fluoride is treated with adsorbent dose, that is 6 gram per liter. Now the percentage removal of fluoride here is 70 percentage, and calculate the specific uptake. So specific uptake, or you need to calculate the adsorption capacity, which I had given to you as it is nothing but milligrams of pollutant adsorbed per unit gram of adsorbent. Okay, so um, there is one formula for this to calculate. So that is nothing but Q equals to C naught minus C equilibrium. C naught here is the initial adsorbate concentration. C is the final or equilibrium adsorbate concentration in the solution. So here it will be water. Okay, so water is having fluoride. So pollutant here is fluoride. So C naught here is the initial fluoride concentration, which is 20 milligram per liter. And final concentration, you can say it is given to you as 70% removal is there. So 70% of 20 milligrams per liter of fluorine is removed. So you can say final concentration will be 1 minus zero point 0.7 into 20 milligram per liter equals to Ce, right? So this will be the amount of chlorine which is remaining in the
6.
solution. Okay, so this is 6 milligram per liter. Now, per so the formula is C naught minus Ce divided by amount of adsorbent in gram per liter. Okay, and here the concentration should be in milligram per liter. So the amount of adsorbent in gram per liter is given to you as 6 gram per liter. Okay, so if you just put up the values, so it will be C naught is 20 milligrams per liter minus Ce is 6 milligram per liter, and the dosage is 6 gram per liter. So if you calculate, this should come out to be
2.33.
2.33, and unit is milligram per gram. So in any numerical, it is very important to mention the unit, because otherwise what this denote is of no use. So every time you do not forget to mention the unit. So here you can say that 2.33 milligrams of fluoride is adsorbed per 1 gram of adsorbent whichever is used, right? So this is the amount it can absorb, right? So that's it. I hope it is clear till now.
Yeah.
So yeah, that's it from my side today. If you have any doubt further, then you can ask, or we can end this session. Okay, so if not, I will end this session. We will meet in the next class. Thank you everyone for
Thank you.
joining.
Thank you.